Hello and welcome to lecture number 12. So in this lecture and in the next two lectures, that is lecture number 13 and 14, in these all three lectures we are going to talk about the liquid-liquid interface. Now in this liquid-liquid interface we have basically two parts. The first part is called the adsorption and orientation at the interface. So before we learn more about liquid-liquid interface, we have to learn about certain properties at the interface. Then our next part 2 would be the discussion on emulsions and microemulsions. Okay, so today here we start with the topic adsorption and orientation at the interface. So naturally the question arises, the adsorption and orientation of what? Okay, so let's come to the point. We can think about certain like small chain, small hydrocarbon chain fatty acids or certain small chain alcohols. Okay, so the functional group here is carboxylic acid group and alcohol means OH. So these kind of molecules can be represented something like this. So why I am representing like this? Because the molecule can be divided into two parts structurally. So the part that contains the hydrocarbon chain, basically this part contains CH2X. Alright, so X could be an integer. Usually X becomes more than 4, 5, 6, 7, 8, 9, 10, whatever. And so this part is hydrophobic. Okay, and that part is basically contains either your carboxylic acid group or alcoholic group. So this part is polar, and if we consider interaction with this molecule with water, so definitely this part becomes hydrophilic. So therefore this hydrophobic part sometimes called as a tail, okay, and this polar hydrophobic part sometimes is called head group. So therefore these kind of molecules have something in common. Okay, so what are the common things? So common things, definitely structurally they have a polar head group and a hydrophobic longer tail or chain. This is the number one similarity. And number two, these type of molecules are soluble both in, to some extent, both in water and oil. Okay, then that's a very interesting part. So it goes into water due to its favorable hydrophilic interaction with the polar head group and the water molecules, and it also goes into oil because the favorable interaction between the hydrophobic tail and with the hydrocarbon molecules of the oil. Okay, so now let's think about a scenario that we have taken water here, and this is air or vapor, whatever, and this is water, H2O. So now if I am dropping some of this kind of small chain fatty acids or alcohol, that means we can refer to this type of molecule. So where would they go? So we can think definitely that since they are soluble to some extent in water, so basically we think that they may stay in the bulk water, alright? Or there is another possibility that they may bury just the polar head group inside the water, or we can call it at the surface. They means they can rest their polar head group at the surface, and they protrude their the long tail hydrocarbon towards the air. All right. So this orientation can be logically possible. Now the question is, which at the beginning means there is no this kind of molecules existing in the water or air-water interface. So there are 0 molecules, and now I'm adding one by one. So at the initial stage, which is a favorable situation? So the this kind of molecule staying at the bulk, or this kind of molecule staying at the interface or the surface? The answer is, I would say that this situation, that means the molecule staying at the bulk of water at the beginning, the energetics are less favorable. So this is a less favorable scenario, and the scenario here is somewhat more favorable, because we have a strong non-favorable interaction between the hydrophobic chain with the water molecules. Okay, so therefore if I keep adding more and more this kind of molecules, so we can draw a situation like that. So graphically we can represent that with more and more molecules, we have these molecules will be slowly accumulating at the surface. So this is the bulk, water, W, and this is air. So one observation would be very common, that the accumulation of the short chain fatty acids or alcohol molecules at the interface of air and water, or at the surface. So now scientifically, or in terms of surface and colloid science, whenever we say that these molecules are being accumulated, there is a better, more appropriate scientific word that replaces the word accumulation, and the correct word is adsorption. Okay, so adsorption at the interface or surface. So if one of the phase is air, so it becomes surface. So this phenomena is called adsorption at the interface or surface. So if we now add on more of this kind of such molecules, we can have like more and more surface adsorption. Okay. So now here we ask a very important question, that if we keep adding the molecule from the scenario like this to there, so what happens to the surface tension of the liquid here in water? So let's assume the original surface tension before any addition of any other molecules, the surface tension was denoted as gamma naught. So that is the original surface tension. So now you think about this. Now whenever we have one molecule and we are adding more, so whenever the second molecule comes in, so the surface has to expand to accommodate the extra molecule. Whenever we are adding more and more, the surface needs to gradually expand in order to accommodate more and more molecules. So therefore, we also write in here that, let's write a sentence, that with gradual surface adsorption, or with gradual adsorption at the surface, surface needs to expand. Alright, and there is absolutely no doubt about it. If the surface doesn't expand, the molecule cannot find their place at the surface. So whenever the surface expands, so that means what? Before the surface was under some kind of tension. So now it starts to expand, means the surface starts to relax. So whenever surface tends to relax to accommodate more and more surface active molecules, the surface tension has to drop, and that is the most simple observation we can make out of this situation. So therefore, what happens that the surface tension drops, or surface tension decreases. All right. So therefore, we can start write an equation, that is the gamma, that is the observed surface tension of the system, is equal to gamma naught minus pi. So pi can be denoted, or the pi is simply called expansion pressure. Okay. So it can have the same unit as of the surface tension. So the thing is, so the pi acts in an opposite direction than this gamma naught. Okay. Or in other words, what I can tell that the more we have adsorption, the more surface tension would drop, and we have the more and more expansion pressure. Now, sometimes a situation appears that gamma naught tends to pi. So when gamma naught tends to pi, so that means gamma tends to 0. That means surface tension is not existent. In reality, such situation arrives, and whenever such situation arrives, we call that we have met the condition for formation of something called a microemulsion. Okay, so for a microemulsion to occur, we need to have the observed surface tension is as close to 0. But sometimes it may happen in certain extreme cases, of course that happens for microemulsion, that the surface tension observed, that means this gamma, might be negative. So that means even it may happen that gamma 0 may become smaller compared to the expansion pressure pi. Now, one distinct feature of the pi, that pi depends on this number of CH2, okay, CH2 groups. So if there is more number of N, it has been observed that the pi would increase. So that means if we have a more hydrophobic tail, the drop of surface tension would be much more evident. All right. So now before we proceed further, there is one more question. So is it always true that the surface tension always drops due to addition of these molecules? Now on the contrary, the opposite things happen also, and that is the surface tension may increase. So we can write here surface tension may increase. So in what case it may increase? So definitely it doesn't increase in this situation whenever the molecule gets adsorbed at the surface, because surface has to expand and surface tension has to drop. So surface tension increases mean we have to add certain molecules that tend to go into the bulk, okay, rather than they doesn't want to stay at the surface. So therefore, remember certain electrolytic molecules or electrolytic agent and molecules like sugar, etc. They tend to be hydrated and they want to be solvated well into the bulk. So they always prefer to stay deeper into the bulk rather than the surface. So in those cases, it has been seen that when we add the molecules, surface tension has been observed to get increased. So in those cases, surface tension increases. So bottom line of this discussion that we get that if we add some molecules, then the molecules prefer to stay at the surface or the interface, the surface tension drops. And if the molecules wants to stay at the bottom of the bulk by staying solvated, the surface tension may increase. Now, what type of molecule wants to stay at the interface? The molecules that are having this dual nature, that means that can have a polar hydrophobic head group and a polar hydrophilic head group and a polar hydrophobic tail. All right. So now you may ask that what happens if we do not have the polar head group and we just add the hydrophobic long tail? Wouldn't that stay at the surface and would decrease the surface tension? The answer is not quite, because if we have too many of these hydrophobic molecules, then they would stay phase separated just like oil. Okay, so we'll have a new interface, oil and water, or a hydrophobic phase or a water, something like that. So this situation is unique to the structure of certain molecules, and the structural characteristic is they must have a polar head group and a hydrophobic tail. Okay. So now, interestingly, we want to expand the same concept from air-water to oil-water interface. So let's see how things happen there. Okay, so I'm going to erase the board and wants to extend our discussion to oil-water interface. So let's do that. So here we think about an oil-water interface. Okay, so they are phase separated. There are two phases, and if we add the same type of molecule here, okay, with a polar head group and a non-polar tail, what we can expect that, so this molecule, due to its polar head group, they may stay in the water like this, or they may stay in the oil phase like this, or they may stay at the interface with burying their polar head group in the water and their non-polar tail in the oil phase. So the question is, out of these three possibilities, what possibility would be energetically favorable? Well, it's needless to say the answer is that the most favorable condition or the most favorable orientation at the interface is something like this, where we have a like dissolves like situation. Means its energy would be minimized if it can have a favorable interaction of the polar head group with the water and the favorable interaction between the non-polar hydrocarbon chain with the oil phase, that means with the hydrocarbon chain of the oil molecules. So the molecules now would get absorbed at the interface of such oil and water interface of oil and water medium. So therefore, from this we can write a sentence that is, we would notice a strong adsorption, okay, strong adsorption of certain kinds of molecules. So not all molecules though. For example, if it is a pure polar molecule, we would expect them to be in the water totally. And if it is a non-polar molecule, we would expect them that it would go into the oil phase totally. But whenever it has both the properties like polar and non-polar property, we would expect a strong adsorption of these molecules at the interface. Okay, a situation like that. So whenever we find a situation like that, we call this phenomenon as surface activity, because definitely certain action or activity is going on at the surface or interface. We can call it the interface activity also. But anyway, sometimes we prefer the surface activity because we mostly study these systems in this kind of science in the water. So the other phase is the air. So we mostly talk about the surface. So certain molecules, they show the surface activity. We call them surface active agents. So the molecules that show surface activity is also called surface active agents. Okay. Now these three terms, means these three words, surface active agents, can be shortened down by a single word, and that single word can be, so we can think about, we take these first four letters, surf, and then we take the three letters here, ACT, act, and perhaps we take this A here and NTS over here. Okay, so what assembly of letters we get? We get surf, act, ANTS. We get surfactants. All right. So now I am using the word surfactant. So far I have been telling like this molecule and that molecule, this type of molecule having polar head group, non-polar tail. But from this point onward, I would always refer this molecule as surfactants or surfactant molecule. So now immediately we came to know that the meaning of the word surfactants means the molecules or the certain types of molecules, means they have to fulfill certain criteria, and the criteria has been already described here. So molecules with certain criteria are only active at the surface or interface, and that's why it's called surfactants. So the question is, now what happens to the surfactant if we keep adding on the surface? Okay, so can we keep them adding forever? Obviously it is no. The answer is no. So what would happen? That is the question. So definitely we'll come to that point, but before that I want to, or we want to make ourselves introduced with the word surfactants in a better way. All right. So primarily there are four major types of surfactants. Okay, so I can write them as 1, 2, 3, and 4. And so let's describe these four types one by one with some examples. Okay, so let's start with, so the surfactants can be anionic and can be cationic, can be non-ionic, and the number 4 types, it is also called amphilytic. Okay, so let's go one by one with certain examples. Anionic means the polar head group is anionic. So an example of this thing is called, in short, SDS. It is also known as sodium dodecyl sulfate. So the dodecyl means 12, and sodium dodecyl sulfate means it has a 12 carbon long chain, and then a sulfate group, SO4 minus, and then Na plus. All right. So you see the polar head group is sulfate, SO4 minus. It is anionic. And this SDS, sodium dodecyl sulfate, has another name, is also called lauryl sulfate, because this C12 long chain COOH means this C12 long chain fatty acid is also called the lauric acid. Okay. And the cationic surfactant, so an example is CTAB. In short, we can call it CTAB. It is cetyl trimethyl ammonium bromide. So it is CTAB, cetyl means 16, so it is 16 carbon chain, and then we have trimethyl ammonium. Okay, so we have this methyl group, 3 methyl groups, and we have C16 means hydrocarbon, and methyl ammonium. Okay, trimethyl ammonium. So the center atom would be nitrogen, so obviously it would be positive, plus bromide, Br minus. So that's why what we call it cetyl trimethyl ammonium bromide, CTAB. It's a cationic surfactant. And then we have non-ionic surfactant. So its structures are complex, I cannot draw. So the examples something like twin and or polyethylene oxide. All right. So polyethylene oxides, basically these are kind of block copolymers. So it's something like it has a long tail hydrocarbon chain, then some oxygen and ethereal linkage, and we have again some hydrocarbon group, again oxygen and some long tail hydrocarbon. So this part can act as a polar head group. All right. So just a second. Okay, so here the ethylene oxides groups acts as a polar head group, and we have, and these are non-ionic. All right. So we can. There are many types of different types of polyethylene oxides. Later we can talk about it. And then there is amphilytic surfactant. So amphilytic means a surfactant where both the cationic as well as anionic groups would be there. Both cationic as well as anionic. And these are mainly observed in amine types of surfactants. Means some kind of polypeptides maybe. Now the thing is, it would behave as a net cationic or anionic, depends on the ambient pH. Okay, so just like the isoelectric concept of isoelectric point of the proteins. So so that's the example, or means the definition. That's the definition of amphilytic surfactant, and the example is something called Dodecyl butane. Okay. So Dodecyl butane. Okay. You can check the spelling later. I may have some doubts. So now coming back to the types of the surfactants, this SDS, sodium dodecyl sulfate, I'm sure you have used it already without even knowing, because this is the most common surfactant that you will find in soaps, hand wash, body wash, and detergent powder for washing clothes, for washing utensils. Okay, so this is the cheapest commercially available surfactant, and this one cationic CTAB, it's mostly used in the chemical laboratory So it is cytotoxic, it has a strong germicidal effect, antibacterial effect, but this is expensive, all right? And non-ionic surfactants, tooling PU, sometimes toolings and etc. Those are available in commercial detergents. It depends on the application that you want to employ. And amphilitic is not so common, but it exists. So from the word surfactant, can you guess one commercially available thing that is related to the activity of surfactant? So I'm talking about, if we just take these first four letters, then we get something probably you now recognize, not from the word but by its action. Yes, it's a very popular detergent brand, and its name sounds very appropriate because it contains a lot of surfactants, namely SDS, and there are other things. So the name sounds appropriate because the application of surfactant is just to remove dirts. So now here we come to a point that if the surfactant molecules are represented like this, so then how can it remove dirt? Well, sometimes means there is a situation where these kind of molecules form a self-assembly, and this self-assembly is known as micelle or surfactant micelle. So the action of the surfactant micelle is to remove the dirt, the greasy part that doesn't go, that is not miscible in water and doesn't go in water phase, but the surfactant molecules can actually hack them away. So therefore, from this action, probably the manufacturer opted the word surf. It's from a scientific perspective that it is property-wise, its action means the cleaning action, and from the name, that is the surfactant. So the bottom line is the surfactants can help us to clean some greasy or oily substance that are otherwise immiscible in water. Okay, so let's come back to the point that when we add the surfactant to water, so what happens to that? So what would be the orientation at the interface? So let's quickly discuss that. So we have water, and this is the air-water interface or surface. So we are adding some surfactant molecules. So at the beginning, from our understanding so far, we now see, or we can easily acknowledge, that the surfactant molecule would orient in the interface just like that. It's polar head group facing water. Now the question is, if I keep on adding more and more surfactant molecule, what would happen? So definitely there would be a time point would come where there would not be any extra more or any extra space at the surface to accommodate more surfactant molecule. Okay, so at this situation we would have a monolayer of surfactant at the surface. Okay, now the question is, if I still add some more surfactant molecule, what would happen? Okay, so that's the question. Now before that, we would like to tell you that if we add those surfactant molecules and try to study some basic physical properties, for example surface tension, and if the surfactant molecule is ionic like SDS, anionic, whatever, then the surfactant may behave as a usual electrolyte molecule, So therefore we can measure the conductivity or any other electrical properties of the solvent. And if we do so, then what will happen? So therefore we try to make a graph plot over here. So on the x-axis we plot the concentration of the surfactant molecules, okay, and in the y-axis we write some physical parameters, okay. So let's start with say surface tension. So at the beginning, when the concentration of the surfactant molecule is 0, we had certain surface tension. So as we keep increasing the concentration of surfactant molecule, we will see the surfactant the surface tension would start to decrease linearly with the increase of the concentration of the surfactant. But if we still keep on increasing, after a certain point we see the surface tension would not is not changing anymore, so it is means just constant. So if we draw the line, so it would behave like this. So linear drop, and then it becomes parallel with the x-axis. Similarly, if we try to measure the conductivity, electrical conductivity, so at the beginning the electrical conductivity would increase, but after a certain concentration the conductivity doesn't change, so it becomes almost parallel with the x-axis. So therefore, if we study these changes, we would see there is certain well-defined concentration beyond which these obvious physical parameters that are supposed to change with the increase in the concentration of the surfactants do not change anymore. They stay constant, almost constant. So this concentration where the changeover, the tipping over occurs, we call this concentration as critical Micelle concentration, or in other words we can call it CMC. It's an abbreviation. So what happens beyond CMC and before CMC is something like this. So before we reach CMC, the surfactant molecules would start to accumulate or would get adsorbed at the interface or at the surface. So it would go on till there is no more space. That means till there the monolayer is complete. Now once it is complete, after that if we add more surfactant molecules, nothing will change, means the conductance or the surface tension or the osmotic pressure, etc., would not change anymore linearly with concentration of surfactants. Therefore, beyond critical Micelle concentration, we have a formation we can write like beyond CMC, we have a formation of an organized aggregate, and this aggregate is also known as self-assembly. Self-assembly of the surfactant molecules, and these aggregates are known as Micelles. So what we can expect here now, that beyond certain concentration, and that exact concentration actually is a limiting point, and that basically defines that yes, a saturation point has come where there are no more space on the surface. So all the surface active molecules are sitting at the interface, and the adsorption of the monolayer is complete. So then therefore we can expect that since this is water, So the hydrophilic molecule part or the polar head group would face towards the water, and we have a self-assembly where the hydrophobic group would hide body inside a pocket. Okay, and outside the pocket the hydrophilic group would be there, and that would interface the water molecule. So we have a certain self-assembly, and the self-assembly may not be spherical always, could be other different interesting shapes, and that we will precisely talk about in the next lecture. But the self-assembly is called micelles. And remember, the formation of micelles or self-assembly is the sole target of the detergent molecule. So whenever we buy any detergent, be it soap or hand wash or detergent for washing clothes or utensils, we have to have those surface active agents, and we want to add them at a concentration. Those concentrations should be equal to or more than the critical micelle concentration, so that getting into water immediately they form the micelles, self-assembly, and they interface water. That means they are very miscible, soluble in water, and the hydrophobic pocket inside would easily capture the grease or oily substances that do not go into the water. So they captures the dirt inside the micelle, and then they are washed away with flowing water and gets removed from the system, and that's how the detergent action works. All right. So we are now familiar of the two terms, that is micelles and critical micelle concentration. But before we finish today's lecture, I have one more question to you. That is, suppose we have an oil water dual phase. So this is oil and this is water, and I am adding to these surfactant molecules. So definitely we would expect that at the critical micelle concentration, or we would reach at a concentration where we have all the all the added molecules to form a monolayer, and there are no more space available at the interface. Okay, good. So now the question is, if I add some more surfactant molecules, so how would the surfactant molecule behave? All right, so that is the question. So think about this. I am just rephrasing the question once again. So I am rephrasing the question for you, means I'm paraphrasing the question. That is, beyond this situation, if I want to add more surfactant molecules, where would the surfactant molecules go? Would they make a self-assembly, that means a micelle in aqueous medium, or they would make a micelle in the oil medium, or they would do something else? Okay, so you just try to think about this, but I will try to address this situation when we would going to study the topic emulsions and microemulsions. So remember, this is a very important aspect. Now before we finish today, one thing I would like to remind you, that if my liquid is an hexane and I have the surfactant molecule adding here, initially the surfactant molecule, you can expect that they would show the surface activity like that by burying their hydrocarbon part just opposite of the water medium, burying their hydrocarbon part in the non-polar medium, and by protruding their polar head group away. So after that, when the critical micelle concentration comes, beyond that, there will be micelle formation. But this time, since this is the hydrophobic group, the micelle formation would occur in reverse manner. So that means the polar head group would be buried inside the pocket or the core, and the non-polar, the polar head group would be buried inside the core, and the non-polar tail would be interfacing the medium. Okay, and this kind of micelle is called the reverse micelle, or the other type that we drawn here just before, it's called the micelle or normal micelle. So whenever we call normal micelle, it means the polar head group interfacing or facing the aqueous layer or the polar medium, and reverse micelle means the non-polar tail or hydrocarbon chain facing the non-polar medium. Okay, so we finish it up here for today, and in the next lecture we will study a little bit more details on the properties of the micellar cell assembly. All right, so stay put, and we'll see you in the next lecture, lecture number 13. So till then, goodbye.